Today we study vectors, the vectors and their components. First, a scalar is a physical quantity that has only magnitude. In physics, we use a scalar and a vector. The difference between the scalar and a vector is a vector has the magnitude, both the magnitude and direction. Scalar has its own magnitude only. Sure, scalar has its own magnitude, and sometimes it has a sign, signature. It has may have a direction, but that direction is not on a plane or in the space. Its direction is just one-dimensional direction. So we say scalar has only magnitude. So mass, length, time. Mass, length, time, temperature, energy. These objects are scalar. We also have a vector. Vector has a magnitude and direction. The most fundamental vector is the displacement. The displacement is we have one point and the other point. This is called the displacement in space. And there's velocity is also vector. Displacement is called the delta x. We put an arrow on top of x. Delta x is displacement, it is a vector. And this is actually the difference of two vectors, x2 minus x1. This is the initial position and the final position. And this difference or addition or subtraction is a vector if x1 and x2 are both of them are vectors. And if we multiply some scalar to this, for example, we divide this one by delta t, and we call delta t is time difference, and we call this time is a scalar. So if we multiply a scalar to a vector, then we obtain another vector. So the velocity, delta x over delta t, is also a vector. So velocity is a vector. And we know that the mass is also scalar. If we multiply this mass to the velocity, then what we obtain is mass times velocity. This is called linear momentum. So linear momentum is also a vector. In this way, we can take the time derivative of both sides, then we obtain force, that is mass times velocity is time derivative of acceleration. So force is mass times acceleration, and acceleration is the velocity difference divided by time difference. So velocity is a vector, velocity difference is also a vector. Therefore, delta v over delta t is also vector. Thus, acceleration is also vector. Here, we know that the mass is a scalar. So, scalar multiplied to a vector is a vector. So, scalar multiplied to a vector is another vector. So, force is another vector. If we express a vector, we use a character and put an arrow on top of it. Or sometimes we use bold-faced the italic letter to represent the vector. If we draw a vector from the starting point to the end point, we connect the 2 points as a line and put an arrow on. And we call this is tail, and the final destination is called head. A vector A is written in the form sometimes from the starting point, end point B, and put an arrow on top of it. If two vectors are called equivalent, then mathematically we write it as A equals B. If A equals B, because a vector has both magnitude and direction, they must be the same. The arrow representing a vector A and another arrow that is representing vector B should be the same if we make a translation. Translation is keeping this line parallel, shift a point and all together, keeping the angle with respect to any other straight line, keeping the same, then we call it as translation. When we translate a vector to another vector, if we find that these two are parallel and the length are the same, then we call two vectors are equivalent. So, as is written in here, if one of them can be translated to be exactly overlapped onto another. There are many vectors, and these vectors are algebraically correlated, and we call a vector space a set of all possible vectors that we are interested in. For example, in the displacement vectors are expressed in terms of three coordinates, three Cartesian coordinates, x, y, and z. In that case, we choose three basis vector that is called I hat, that is along the x-axis, and j hat, that is unit vector along the y-axis, and k hat, that is the unit vector along the z-axis, and multiply x, y, and z, three scalars. We call this as a linear combination. This is a kind of three-dimensional displacement vector. Vector space in three-dimensional vector space can be expressed as a linear combination of three linearly independent vectors, and these three are called basis vectors, or this plural basis. And we have the three scalars. They are called components. So x is x component, y is y component, and z is z component. And I hat, j hat, k hat are all basis vectors. Basis vectors are linearly independent vectors. And number of linearly independent vectors in a vector space is called the dimension. In three-dimensional space, we have the three linearly independent vectors. In two-dimensional space, we have I hat and j hat, two linearly independent vectors. If we add two vectors, this is how to organize the summation of two vectors, translate a vector in this way, then you can add A to B. In this form, you have added B to A. So in either way, A plus B equals B plus A. Therefore, this summation of two vectors is commutative. You can change the order. These are the explanations how to add two vectors. We have another word, coplanar. Let's read it. The three non-zero vectors A, B, and A plus B, we have A vector and B vector. This is A plus B vector. They are making a triangle. The triangle is always on a single plane, so they are coplanar. Together. They are on the same plane, so we call these A, B, and A plus B are all coplanar. And as we have already stated, the addition of two vectors is commutative. So A plus B equals B plus A. Addition is also associative. You can change the order of addition. So you can add A plus B first and then add C to A plus B. Or you can add B plus C plus first and then add B plus C to A. These two values are the same. So we say this is associative law. In magnitude, we have either A or bold-faced A, and magnitude is expressed as an absolute value of a vector. So that is a length of a vector if we draw the vector in an arrow form. If we multiply a real number to a vector, it is always another vector. In case we multiply positive number to a vector, then a vector changes its sign. This is A. If I multiply x, in this case, they are parallel. That means the length is shorter than A. Therefore, this x is between 0 and 1. And this length is greater than the length of A. Thus, the x is greater than 1. On the other hand, if you flip the sign of x, then the direction is opposite. So, if x is less than 0, then xa is anti-parallel, or we can say it's opposite to A. So magnitude of a vector is written in this form, and after multiplying a scalar, the magnitude is an absolute value of that scalar x multiplied by the magnitude of A. There's also distributive law is effective to do scalar multiplication to a vector. This x and y are scalar, and A and B are vectors. So distributive law works if we multiply the addition of scalars or addition of vectors to a single scalar. Zero vector is also called a null vector, and that is algebraically additive identity of vector addition. we have already studied that multiplying a scalar to a vector is another vector. And if we multiply -1 to a vector, you will find that according to this distributive law, a plus minus a is always 0. So the minus a is additive inverse of a vector a. If you study a vector, we not only add or subtract or multiply scalar numbers, but also we multiply two vectors. There are two kinds of vector multiplication. The first one is the scalar product. Scalar product is the product of two vectors whose result is a scalar. Let's see. A dot b of two vectors, scalar product is defined by the product of two vector magnitudes of the two vectors multiplied by cosine theta. This theta is the angle between the two vectors. Here we find it. A is a vector, B is another vector. There's angle between A and B. You know, cosine theta equals cosine pi minus theta. Therefore, am I right? Cosine minus, let's see, theta pi minus theta. Minus. Okay, eraser. So what we find is we first multiply the magnitudes of the two vectors, and then we multiply cosine of the angle between the two. So the angle between the two represents the angle, smaller angle. We have this angle, and we have another angle. Anyway, A times B times cosine theta, where theta is the angle between A and B, we can rewrite this one as A times B cosine theta. And this is length of A and B cosine theta. We make a right triangle, and this length is B cosine theta. In a similar manner, we can multiply the magnitude of B, and we have A. We can make right triangle, the same angle theta, and this length. The whole length is B, and this length is A cosine theta. So this is a projection of A onto B. Okay. So scalar product is a scalar, and the projection is maximized when A and B are parallel. It has a magnitude the biggest when they are both parallel or anti-parallel, but it is always vanishing when A and B are making a right angle, because the cosine cosine half of pi is always 0. Okay? We use hat. We use a hat to identify a vector parallel to any vector to represent the unit vector along that vector. That is to multiply the inverse of the magnitude of a vector to a vector. As we have already studied, there are 3 linearly independent vectors in the 3-dimensional Euclidean space, and the 3-dimensional Euclidean space can be described easily in terms of the Cartesian coordinates. The basis vectors in the Cartesian coordinates are usually selected as I, J, K. We use the hat to represent the unit vectors along the x-axis, along the y-axis, and along the z-axis. This is a multiplication table for the scalar product of 3 basis vectors in the Cartesian coordinate system. Because I hat, j hat, k hat are all equal in magnitude, that is unit vectors, 1, and all 3 of them are perpendicular to among one another. So any pair can make a scalar product. For example, II, JJ, and KK. If we multiply to find the scalar product of itself, because the magnitude is 1, they are all equal to 1. If they are different, for example, IJ, IK, JI, JK, KI, KJ, if they are different, the scalar product is always 0, because x-axis, y-axis, z-axis, the unit vector along the x-axis I hat, unit vector along the y-axis j hat, and unit vector along the z-axis is k hat, they are all making a right angle. So cosine theta between any 2 different unit vectors in the Cartesian coordinate system, unit basis vector, they're making a right angle, right angle. Therefore, the scalar product is all equal to 0 when they are different, all equal to 1 when they are the same. In this way, we can carry out the calculation further. For example, if I multiply A dot B, then we say AX, BX, AY, BY, AZ, BZ. Because scalar product of A dot B can be expressed as this A is AX I hat, AY J hat, and AZ K hat, right? And the B vector, BX I hat, BY J hat, and BZ K hat. If we make a scalar product, non-vanishing term is composed of the scalar product of I and I, J and J, and K only. Therefore, the scalar product can be expressed in terms of Cartesian coordinates, product of x component, product of y components, product of z components, and then add them up. We can make use of Pythagoras' theorem what happens if I compute a squared? Then a squared is, this is only for the two-dimensional case. In three-dimensional case, a squared is ax squared, ay squared, az squared. Okay? The length of a vector is the square root of this. So in case we have this vector on the xy plane, the magnitude of two-dimensional vector can be expressed in this way. Here we have three-dimensional case. Ax is the x component of vector A. Ay is y component of a vector. And az is the z component of the vector A. As I already told you, scalar product between two vectors can be expressed as a sum of products of each component. The scalar product of itself is a square, and the square is the square of the magnitude. For vector square, a vector square is defined by scalar product with itself, and that is just the same as square of magnitude. In three dimensions, a point x on a plane perpendicular to the unit vector n is parameterized by this linear equation. Here's a plane. We have a normal vector that is perpendicular to this plane. I have the origin. This is a vector, fixed constant vector. Constant vector and arbitrary point x. And the difference between x and a is x minus a, right? So because n hat is perpendicular to this plane, any vector on this plane is perpendicular to this unit vector n hat. Therefore, scalar product between x minus a and n hat must be 0. Okay. Let's say number 12. Let a be a vector and n hat be an arbitrary constant unit vector. The a can be decomposed into two pieces. Here we represent A parallel. A parallel is a vector component parallel to n. Parallel to n hat. Parallel. And we use a perp that is perpendicular to n hat. So, we overlap the tails of the two vectors A and n hat. Then we can always find a single plane because they are making a triangle. And we make a projection of this point onto the straight line extending the unit vector and hat. This is a foot. The straight line connecting the head and the foot must make a right angle. Then you will find that a parallel should be the projection of A onto the unit vector and hat. And this is a right triangle. So if we add this parallel component and perpendicular component, this parallel component is a parallel and this perpendicular component is a perp. If we add these two vectors, then we end up with the original vector A. Alright? So, let's see. If I multiply a parallel as a scalar product with n hat, what we find is A dot n hat and n hat dot n hat. Because n hat is a unit vector, it is 1. So, scalar product of these two must be the same. Because it projects out the parallel component along the n hat direction only. Therefore, this is expressed in this way. What happens to the perpendicular direction? It is easy to find that this vector should be expressed as a sum of these two vectors. This is a vector and this is a minus a parallel vector. So a minus a vector minus a parallel is a minus a parallel. We copy this. A dot n hat n hat. Oh, that's the reason why we have perpendicular component is written. It can be expressed in this way. Let us consider a circle. Angles are formed by drawing lines from the ends of diameter of a circle. This is a circle, and this is a diameter. This radius, we have 3 radii. A, vector V, and vector C are 3 radius vectors. And capital A, capital B, if we connect, then the center O is along the straight line, on the straight line AB. That means the line segment AB is a diameter. Alright. We know that the angle, this angle, is a right triangle. We can prove this in a very easy way if we make use of vector notation. Let's see. A, B, C are 3 vectors. A, B, C are 3 vectors from the center A, B, and C to the 3 points A, B, C of the circle. You know, A, B, C are all radii. Therefore, the square of A, square of B, and square of C are all radius squared. Because AB, straight line AB, line segment AB is diameter of this circle, what about computing A minus B? This is A. This is A. This is B. So minus B is here. So this is A minus B. So diameter itself is A minus B. Here, what we want to show is that C minus A and C minus B, they are making a right angle. Then, what we have to do is, if they are right angle, cosine 90 degrees is 0. What we want to prove this is, that means that what we want to do is compute the scalar product of C minus A, C minus B. And if we end up with the result, if it's 0, because C minus A, C minus B, both of them are non-vanishing vectors, the scalar product vanishes only if the angle between these two vectors are right angle. In this manner, we compute C minus A, C minus A, and C minus B. But here, AC, what is that? AC. C minus AC. AC. This is a C. This is A. So C. This is A. So this is minus A. So C minus A. That's right. And this is C minus B. C. This is B. So this is minus B. So this is C minus B. Right? C minus B. But we know that A and B are equal in magnitudes and their directions are opposite. So A plus B equals 0. A plus B equals 0. So B equals minus A. So we can replace this minus B with plus A. So this is C plus A. If we make a scalar product of these two, then C minus A dot C minus B. But C minus B is replaced with C plus A. We can make an expansion. Then we have C squared minus A squared. You know, A, B, C, all of them are ready. So A squared here, A squared, B squared, C squared, all equal to R squared, where R is the radius. Therefore, C squared minus A squared equals 0. That means these two vectors are making right angle. The unit vector n hat that makes the angle 45 degrees with both I and J is have x-axis, y-axis. We have I hat 45 degrees. So the vector should be along this direction or this direction. Okay? There is ambiguity. This is possible. This is possible. And y-axis, unit vector j hat this will make 45 degrees relative to the j hat. This will make 45 degrees with respect to x-axis. Okay. Number 15. Consider an arbitrary point on the xy plane. So this is the x coordinate and y coordinate of this two-dimensional vector. We consider a circle on a circle of radius r. So this radius is r. And an xy plane whose center is at A. So this vector is A vector is the position vector representing the center. Any point on a circle, this is x, the point, the center is A, the displacement from the center to that point is x minus A. The radius is x minus A, absolute value equals r. Why don't we square this? This x minus A squared equals r squared. This is the equation representing a circle whose center is at A and radius is r. Next, we consider some rotation. We have usual basis vector, the xy plane, x-axis, y-axis. I hat is the unit vector along the x-axis. J hat is the unit vector along the y-axis. And we want to make a rotation of this Cartesian coordinate system. So we have another axis that is called x prime, y prime. And unit vector along the x prime axis is I prime. Unit vector along the y prime is j prime. And we have angle theta. We can find the rotational matrix that transforms the coordinates of, from xy axis and to x prime y prime axis by making use of the scalar product of these unit vectors I hat, j hat, and I hat, j hat, and I prime hat, j prime hat. Let's see. The angle between I and I prime equals, this is a theta. So this is a cosine theta. I dot j at prime equals, we have I is here, j prime is here. What is the angle? That is cosine I plus theta. This is cosine this is vanishing. Let's see. I is here, I prime. They are making angle theta. That's right. That's right. Let's do it again. This one first. I have I and I prime. This is the angle theta. I prime this one equals magnitude by prime and cosine angle between I and I prime, cosine theta. Right. So this one is 1 times cosine theta. That's a cosine theta. That's right. Next one. Why don't we consider this one? We have J is here, and then I prime is here. You know, this is I, so this angle was a theta, so half of pi minus theta. So we have J times I prime. J scalar product with J with I prime is cosine. That's right. And again, this is 1 times sine theta. Right? So these two make a scalar product with cosine theta, and these two make a scalar product with the sine theta. And both of them are positive. Both of them are positive if theta is in the range from 0 to half of pi. The next one, we consider J. We have J prime here, J and J prime. They are making angle theta. So J dot J prime equals, again, 1 times the angle between them is cosine, is theta, so this is cosine theta. So at last, we consider this one, I prime, that is making a right angle theta with respect to I, and what we are interested in is J prime. This is the right angle. This is right angle. This one is J hat prime the I. This one is this angle is greater than half of pi, so cosine this one. This is minus sine theta. We can expand this cosine minus sine and cosine half of pi vanishes, so this one vanishes and this one is 1, so we have minus sine theta. We have a vector A and we would like to rotate this vector by an angle of theta. Then we end up with the finite components of this A prime in this way. It is a little bit tricky, but most of you may have been acquainted with this if you have taken the mathematics course. Let's see. We combine all these results all together to construct this relation. Okay, let's see. I and I prime, they make cosine theta. Okay, if I multiply I to this expression, what we find is because I is orthogonal to j, so what we have is cosine theta. So I hat prime is cosine theta. That means this vector represents this. The next one, if I multiply j to I prime, what we have is just a sine theta. Why? J to I prime scalar product is just a sine theta. So we just copy this result in here. What happens to this case if I multiply I to j prime here? What I to j prime, what I have is a minus sine theta. Just minus sine theta is in here. Lastly, if I multiply j hat to j hat prime, where is j hat prime? J to j hat prime, the result was cosine theta. J hat to j prime, cosine theta. So this is the master formula, right? Let's copy this. I prime Alright. First of all, the vector A was ax I hat plus ay j hat, right? If we rotate by angle, what you find A is axi prime ay j prime, because this is I and this is j. After rotation by an angle theta, this is I hat prime, this will be j hat prime. So the components will be the same with respect to the each basis vectors. Hence, what we can do is just substitute these results in here. I prime I cosine j sine, j prime minus I sine and j cosine. Substitute these two values in here. In here, ax I cosine j sine plus ay minus I sine plus j cosine. If I expand this, all these results, components proportional to I. Ax cosine theta here minus ay sine theta. Components j component ax sine theta and J becomes AY cosine theta. That these two are the same as this result. So this is the final result for the coordinate transformation. In such a manner, we can find these following results, and you can follow up in a similar manner. There is another multiplication called a vector product. The cross product or vector product. We have two vectors, A and B. Then A and B makes always on a single plane. After translation, we overlap the tails of A and B. And you will find the normal vector. There are two normal vectors on the plane. This is A cross B, and this is B cross A. So you swipe your fingers from A to B, and your right hand thumb is heading toward A cross B. Your fingers right this right handed screw rule. This is A cross B, and cross product is anti-commutative. So A cross B and B cross A, they are opposite sign. A cross B and B cross A. So this is the multiplication table for the cross product. If they are parallel, the results are all vanishing. The only surviving term is a perpendicular component. For example, I have x-axis, y-axis, and z-axis. So I is here, J is here, K is here. I cross J is K. J cross K equals I. K cross I equals J. And then we replace the order. We flip the order, then you have negative sign. IK minus J. IKI plus J. IK minus J. JK plus I. KJ minus I. Next, we consider a triangle. We have vector A, vector B. There's an angle between A and B. So area of a triangle can be expressed in terms of 1/2, magnitude of A, magnitude of B, and sine theta. Right angle, so it's A and B sine theta. Or B theta, right angle, A, B times A sine theta, multiplied by 1/2. That is the area of a triangle spanned by two vectors. Why don't we consider the area of a parallelogram? They have parallel. Okay? So area of a parallelogram is exactly the same as the area of a triangle, except that we do not have a factor 1/2. Next, by making use of this multiplication table, we can simplify the expression for the cross product of the two vectors expressed in terms of Cartesian coordinates. The result is we shall find that it is expressed in terms of determinant I, j, k, ax, ay, az, bx, by, bz. So I component, then we make a determinant of this. So I equals I, ay, az, by, bc. J K az, ax, zx, bz, bx, k, ax, ay, bx, by. So this value is ay, bz minus az, by. The second term, az, bx minus ax, bz. The third term, proportional to k hat, is ax, by, ax, by, by, ax minus by ax. This is called the parallelopiped. This is a parallelogram. This is a triangle, parallelogram, and parallelopiped. The volume of the parallelopiped is expressed as the absolute value of the triple scalar product. We can also write it in this way. We never multiply the scalar product first. We multiply the cross product first and then make a scalar product. And this is after taking the absolute value, we'll find this one is the volume of the parallelopiped. This is based on the Pythagoras theorem, sine squared theta plus cosine squared theta equals 1. It is straightforward to find that this one is related to, we multiply a vector, b vector squared. We mean a cross b, absolute value squared. This is a squared b squared sine squared theta, where theta is the angle between a and b. A dot b squared is a squared b squared cosine squared theta. So we make use of this to verify this relation. The law of sine can be derived by making use of cross product very easily. A cross b, b cross c, c cross a. Use this. Consider two unit vectors A and B that can be obtained by rotating up. This is quite similar to the relation that we have obtained for the rotation of two basis vector set I, j into I prime j prime. We can apply this one to re-express this relation for number 11. So this is another way to verify the addition rule for cosine and sine. We can make use of a scalar product and cross product, vector product, to verify the addition law of cosine and sine. Later, we will also consider by making use of complex numbers to verify this relation too. Law of cosine can also be derived very easily by making use of a vector. You can follow this straightforward computation shown in number 13. This is related to right triangle, and Pythagorean theorem derives straightforwardly. There is a problem. This problem is related to the area of a triangle, and perhaps you already know about this Heron's formula for the area of a triangle expressed in terms of the side lengths of a triangle. A triangle is given here, A, B, C. These three numbers represent the side lengths. One side, two sides, three sides, and A is the side length of this side, B and C. And area of a triangle can be expressed as in terms of cross product. We have considered this one already. And here, area of a triangle, it can be expressed as in terms of cross product. However, that one can also be expressed in terms of the side lengths A, B, and C. And we'll find that the area is completely factorized as a function. And the well-known function is called the Scalar function. You can find this Scalar function is expressed in very special form. And any high school student can factorize this expression into this. You will find this is sum of the three side lengths, sum of two subtracted by the other, and cyclic rotation. A plus B minus C, B plus C minus A, C plus A minus B. We'll find that this is positive for the three side lengths, and every vector is positive, so this is negative definite. So we have area of a triangle can be expressed as 1/4, 1/4 of the square root of minus Scalar function. You'll find very good information from this paper by clicking. Click this. Something wrong. In the PDF file, you can click this result, and then you will find that there is a good derivation about this. Okay, that's it for today.